Today we're going to go over the elimination reaction, specifically the E2. I'm going to begin with a brief overview, then I'll go into the mechanism and Zaitsev's rule, and we'll finish off with some practice problems. So as an overview, the elimination reaction is an alternative to substitution reactions. They compete with one another and it can impact the yield of your product. So for a substitution reaction, you know that your nucleophile replaces your leaving group in the product. Well, in an elimination reaction, what you have is not a nucleophile, but a base, or at least your nucleophile is behaving more as a base than a nucleophile. And instead of attacking the carbon, it's actually going to pull off a hydrogen, and your product is going to lose both a hydrogen and a bromine. Instead, it'll form an alkene. So with the substitution reaction, you're substituting one thing for another. With elimination reaction, you're removing a hydrogen as well as their leaving group to form an alkene. So here's the basic mechanism for an elimination reaction. You have a base, a strong base that pulls off a hydrogen. Therefore, that bond between hydrogen and carbon is going to break, and the electron density is going to move to the carbon-carbon bond. This is going to cause the bond between the carbon and your leaving group to break, and electron density to therefore move on to the leaving group. This is going to result in the formation of an alkene, as this bond is broken, and this bond is broken, and this one is formed. You'll also have a protonated base as well as your leaving group with a negative charge. A couple things to point out about this mechanism. First, it all happens at the same time. So your base attacks the hydrogen while simultaneously breaking the carbon-hydrogen bond, also forming the carbon-carbon bond, and also forming breaking the carbon-leaving group bond as well. So this reaction happens all in one step. There are no intermediates. Another thing to point out is that this hydrogen that is being pulled off is on a carbon that is neighboring the carbon with the leaving group. So the hydrogen that gets pulled off is not any hydrogen in the molecule. It's specifically a hydrogen on the neighboring carbon. We call this beta hydrogen. If the carbon with the leaving group is the alpha carbon, the carbon next door is going to be a beta carbon. If it has a hydrogen on it, that carbon can be deprotonated to form your alkene. Additionally, the hydrogen that is deprotonated is opposite. So we notice this hydrogen is facing up while the leaving group is facing down. So the hydrogen must be anti or in the opposite direction of your leaving group. And lastly, that hydrogen must be in the same plane. So what we're looking for we're looking for hydrogen that are beta, anti, and periplanar. Here's another example of a mechanism where the base is pulling off this hydrogen, breaking the carbon-hydrogen bond, forming a carbon-carbon bond, and your leaving group is falling off. You have a transition state which illustrates which bonds are being broken and formed and how it's all happening simultaneously to therefore produce your alkene, where your base is now bonded to that hydrogen and you have lost your leaving group. One of the important things about the E2 reaction is that it must follow Zaitsev's rule in the product. When you're eliminating your hydrogen and your leaving group from your alkyl halide, the product that is going to form, the alkene that is going to form, is going to be the most substituted alkene. That's going to be your major product. The reason why this is important is because you can have an alkyl halide with multiple beta hydrogens as shown by 2-bromobutane. There are hydrogen on the methyl group. There are also hydrogen on the methylene group. Your base can actually deprotonate any beta hydrogen that are anti-periplanar. However, the major product, the product that is most stable and is going to form in the largest quantity, is going to be the alkene that has the most substituents on it. So in this case, this alkene is bonded to the CH3 group as well as another CH3 group. So it has two substituents on it. However, this alkene is only bonded to one CH2 group. The other substituents are all hydrogen. So the more substituents you have on your alkene, the more stable that product and the more likely that product will form. We can also consider the exact same thing with 2-bromo, 2-methylbutane. Here, there are 3 beta carbon, 2 methyl groups, as well as 1-methylene. And your base can deprotonate the hydrogen on any of these beta carbons. What comes in the greatest quantity is the alkene that is more highly substituted. This alkene is bonded to a methyl group here, a methyl group here, and a methyl group here, making it tri-substituted. Whereas this alkene is bonded to a methyl group here and an ethyl group that's only di-substituted. Everything else that is bonded to are hydrogen. So because this alkene is more substituted, it will be your major product. Even though, I want to point out that there's 2 products here, even though there are 3 options for beta hydrogen, because these are both methyl groups, so they're exactly the same. Both of these, deprotonating either one of these hydrogens will actually give you the same product here. So let's do a little practice to walk through the mechanism as well as look for beta and anti-periplanar hydrogens. There are several problems here. I'm going to switch to the dot camera so that we can see those and do them together. All right. So the first one, we have 1s, 2r, 1-bromo, 2-methyl cyclohexane. And we have our base here that's going to be used to pull off a hydrogen. This base can also be written as the following, where here is your base and it's going to pull off a hydrogen that is anti-periplanar. So first let's look for our beta hydrogen. If we're focusing on our leaving group, the beta hydrogen that we have, this is the alpha carbon, this is a beta carbon, and this is a beta carbon. So we can pull off hydrogen from either one of these carbons. We want to make sure that the hydrogen that we pull off are anti and periplanar, which means if this leaving group is up, the hydrogen that we pull off must be down. In this case, you do have a hydrogen that is down, which means we can pull off this hydrogen to form our alkene. We also have 2 hydrogen here, 1 up and 1 down. So we have 2 options in which we can form an alkene and form our product. So I'm going to show the mechanism for our major product, and then I'll also illustrate what could also be our minor product. Our hydrogen here is anti, but in the same plane. If this is facing up, going out of the paper, this hydrogen is going into the paper, so they're in the same plane, up and down. So we can pull off this hydrogen, push the electron density onto this carbon, and lose the bromine as our leaving group. Therefore, our major product is the following alkene. We could also have a minor product if we pulled off this hydrogen here. This hydrogen, again, is anti to the leaving group. The leaving group is facing up. This hydrogen is facing down. Therefore, they're opposite, but in the same plane, up and down. If we pulled off this hydrogen, we would get the following product. However, this product has an alkene that is more substituted. This double bond is bonded to another methyl, so it has 1, 2, 3 substituents, whereas this alkene only has 1, 2 substituents on it. So this is more substituted. This is going to be our major product. One methyl cyclohexene. Let's look at a very similar reaction. In this case, instead of having 1s2r, we're going to have 1s2s, 1-bromo, 2-methyl cyclohexane. So again, with this elimination reaction, we first find our leaving group, bromine, and we want to look at the beta carbons. We have 2 options for beta carbons. Both of these beta carbon have hydrogen on them. This hydrogen is going up. This one has hydrogen up and hydrogen down. So we already have our beta hydrogen. Now we got to figure out which hydrogen are anti. If we look at this hydrogen here, this hydrogen is facing up, just as this bromine is facing up. So even though they're in the same plane, this hydrogen is not anti, and we cannot pull off this hydrogen to lose this leaving group. We have to pull off the hydrogen here, which is our anti-hydrogen. So in this case, our product, I'll show the mechanism. Pull off the hydrogen, push the electron density to the double bond, lose your leaving group. In this case, we only have one product because we only have one hydrogen that is anti and periplanar. Our product here is S,3-methyl cyclohexene. So although the alkene that could have formed here would have been more stable, we cannot get this alkene because this hydrogen is not in the right conformation. It is not anti to this bromine. They are both facing in the same direction. They're both syn. Let's do another reaction. We're going to use the same base. We have iodine as our leaving group in this case, a very good leaving group. So first we want to identify our beta carbon. This is our alpha carbon. The carbon that's bonded to it here is beta. This carbon is beta. And this carbon is beta. So we have 3 options to protonate the hydrogen, which can give us multiple products. Because the hydrogen here, there's some up and down. We're going to pull off the hydrogen that is anti, which is actually the hydrogen on the dash. It's going to break this carbon-hydrogen bond, pushing the electron density onto the carbon-carbon bond, and then losing the iodine bond. This will give us the following product: methyl cyclohexene, E N B. And this is just a CH3 group, no double bond. There we go. So if you notice here, our alkene is tri-substituted, 1, 2, and 3 substituents on it. If we had pulled off the hydrogen here, we would have ended up with this product. If we had pulled off the hydrogen here, we would have pushed the electron density between that carbon-hydrogen bond to form a carbon-carbon bond here and lost our iodine as a leaving group, giving us this product, which is di-substituted, 1, 2, and this one's tri-substituted, 1, 2, 3. So our major product is methyl cyclohexene. Let's do one last reaction. Here we have 2S, 3S, 2-bromo, 3-methylpentane. We find our leaving group, bromine, and we're looking for the beta hydrogen. There's carbon here with beta hydrogen and carbon here with beta hydrogen. There are many hydrogen here to pull off. The hydrogen here is on a dash. So we want to figure out if this hydrogen can actually react to lose this as our leaving group. And for that to happen, this hydrogen has to be anti and periplanar. In this case, it is anti. It's in the opposite direction. In the same plane, bromine going up, hydrogen going down. And so we can pull off this hydrogen using our base, push the electron density onto the carbon-carbon bond, and lose bromine as our leaving group. This is going to give us E,3-methylpentene. We also could have pulled off the hydrogen here But that would have given us a mono-substituted alkene, where when we pulled off this hydrogen, we ended up with a 1, 2, 3 tri-substituted alkene. So E3-methylpentene is our Mader product because of Zaitsev's rule. So in an elimination reaction, you're losing your leaving group and forming an alkene, and you're doing this by eliminating the leaving group as well as the beta hydrogen that are anti-periplanar. When you're doing this mechanism, you always want to remember Zaitsev's rule, which tells you that you're going to form the more substituted alkene in your product.